Okay, so I just give a short introduction. So this is Leipzig Gophers meeting 21, September 28th, 2021. And we are happy to have Carl presenting on Concise Encoding. So take it away, Carl.
Hey, everybody. Yeah, I guess a little bit of background. I started programming age 8 and loved it. And I was doing a lot of basic programming on a Commodore 64. Started programming professionally in 1997, and I've touched all the way up and down the stack. But my first love and forever love is the low-level stuff. Dealing with device drivers, dealing with bit bashing, dealing with protocols, data communications, and all that kind of stuff. So when I started approaching Go, of course, I took it from the low-level perspective. And one of the things that I've been working on for the past 3 years, no, 3.5 years now, I guess, is a new encoding format that sort of touches the things that I think are really important for a general purpose data transmission medium. So let's see, share my, here we go. So actually, I'll put this in channel. If you guys want to, so if you just want to follow along locally, that's fine. Yeah, so anyway, basically what I'm thinking of, there's a lot of information that I put down here. I don't expect to get through it all. This was just because I don't really know how much is necessary to fill up the full time. So this is going to be kind of just go along, and if you guys have questions or anything like that, just interrupt me. It's totally cool. As I said, I don't expect to get all the way through this. So we'll start off with a little overview of data encoding in general and why I came up with this encoding format, Concise Encoding, a little overview of what it is, how it works. The reference implementation is in Go, of course, which is why I'm doing the presentation. So I'll cover, the overall architecture. I'll have some code examples to sort of show how I've structured this thing as a unit. If there is time, which there won't be, but if there is time, I'll go through the binary codec itself, because it's pretty small, pretty simple, and it'd probably be pretty interesting to have a look at it. So anyway, nowadays there are basically 2 primary schools of thought when it comes to encoding data and sending it between different machines. We have this is kind of loose. It's not a hard and fast definition, but we have basically record-oriented and element-oriented data. The record-oriented data means that you're going to have a bunch of data that's all together and it belongs in one unit. And generally, when you're working at this level, you're talking about sending like a lot of these records, just tons of them. We're talking Google level of data communications. They have, millions, billions of records flying all over the place internally. They don't necessarily care that there's a bit of bandwidth wastage on it. What they care about is they want to get it from memory in one machine to memory and usable in another machine in as little time as possible. And so this is where protobufs and flat buffers and all of those come in. There's a little bit of upfront. You have to do a bunch of code generation. You have a bunch of data definition files and things like that. So there's some headaches up front. But once you get it going, it just does its job, and you generally don't have to worry too much about it. That's what they're all about. Also, a lot of these formats, they tend to try to match the actual memory layout in languages such as C++, so that you can take your struct literally from memory in one machine, boom, move it over to another machine, and it just works in theory. But that's the idea. And so then you can get into situations where you can mmap, like a 5 terabyte file, and you can stream through the whole thing, and you use the operating system's paging system. So the operating system will page these in and out of memory, even though it's sitting in a file. You can pretend that it's just sitting in memory. You access it, everything directly. And this is a really, really fast way to access just tons and tons of data, once again, at Google scale. So this is where these record-oriented formats come into play, and that's where their real strengths are. The other side of the coin is element-oriented. And this is where you're dealing with, ad hoc data, little bits of pieces here and there. And, this user is logging in. Here's their authentication code. Here's their permissions and things like that. Just small little snippets of data that's going to be, well, usually you're looking at about maximum 10K of data transferred at a time, but some people will send up to gigabytes if they really want to. At that point, they're better off using a record-oriented one, but they'll do that. Schema is entirely optional. You're talking like the JSON, XML, HTML, CBOR, those kinds of encoding systems. So it's very ad hoc. You just add some fields into it, and then you add the fields onto the other side, and you publish a little spec and say, okay, here's how you talk to my API. And it's going to be some REST-oriented API that's sending little bits of data here and there. That's what most people do. That's how everybody starts. And they only ever get to this Google scale. Well, very few people ever do. So since this is where most people are anyway, that was where I wanted to be. And that's where I wanted to be with my format. But I wanted to deal with some of the issues that these formats have. One of the biggest one, of course, is lack of types. XML was the worst because it's just everything's a string. JSON fixed that a little bit because they said, okay, we can have strings and we can have Booleans and we can have numbers, but there are some restrictions on what the range of the numbers are. And no, there's no dates. No, there's none of this type. There's none of that type. That becomes problematic because now you have to stringify things. And stringification, when I started looking into just how much time this was taking up, even in the Go libraries, it could take up to 40% of your processing time just to convert to and from ISO 8601 dates. It's really, really bad. So I wanted to get rid of that. Another issue that comes up is that all of these guys, with the exception of CBOR, but all of these guys are all text-based. So JSON, you have to serialize it to text, deserialize it from text. Excuse me. That's very wasteful on the CPU. And also when you're transmitting it, if you're not doing like a gzip encoding or something like that, which is also going to take more CPU, you're wasting a ton of bandwidth, which once again, if you're small, doesn't really matter so much, but as you scale up and up and up and up, that starts to become more and more of a problem. So I wanted to make sure that I could nip this in the bud before it becomes a problem. And then, of course, there's the issue that you have to choose between one and the other. I don't like that. So I wanted to come up with a format where you could have both. You could literally have one text encoding, one binary encoding, convert between the two seamlessly without losing any information whatsoever. And then you have a situation where, as a human, you edit all of your text format, and then you put it into the machine, and the machine just keeps it in binary. It transmits it in binary. The other machine receives it in binary. It stays in binary all the way, unless someone along the way wants to debug it or wants to see the result or whatever, then it converts it back to text. And only then, only when you actually need a human to see it. That's the idea for it. Another issue that comes up a lot is deprecations and changes to the format. So JSON, for example, you can't change the format. If you change the format, it becomes incompatible. There's JSON 5 coming out now that's trying to fix a lot of the problems that JSON has, but it's still, once again, there's no version spec, there's nothing in the document itself that says, this is the spec that I adhere to. And so JSON 5 is going to suffer the exact same problems that JSON did, where as we discover more issues with it and we decide, oh, we should deprecate this. Oh, wait a minute, no, we can't, because there's no way to say, I adhere to this particular specification. So that's where I'm coming from when I came up with concise encoding. It's obviously element oriented. Sorry?
Just a short question, if I may, about the issues in existing formats, lack of types. In XML, you have like the schema where you can say something should be an int or a float or something like that. But I mean, it's serialized as is. You need the schema separately, basically, to validate it. This is
that's basically what I mean. Is these a lot like this? The fix-ups for these were added on afterwards, and you have to use a schema to be able to say, this is actually this, that's actually that. And you can do the same thing in JSON. You can do a schema on that and say, this is an 8601 date, this is a URL, this is a email address, and all that sort of thing. So they kind of work, but it's just sort of this, there's all of these extra layers and more bureaucracy to be able to solve the problem. Yeah. So I wanted something where all of the types are first-class citizens. Okay, yeah. So yeah, concise encoding is record oriented. You can represent it in binary and text. You can transfer between the two with no data loss. It's also tightly specified. That's another thing I forgot to list up on the existing issues. This is a huge problem, and this is going to become even worse as time goes on because we're living in an increasingly hostile world. If you don't very tightly specify your data formats, you're going to have security holes. For example, JSON. You have an implementation in Python, you have an implementation in JavaScript, you have an implementation in C++, in all of these different languages. And as your system becomes more complex, you're going to build certain parts of the system in one language, certain parts in another language, or maybe there'll be multiple libraries that you're using. And each of those libraries are going to have slightly different behaviors. So for example, if you ingest data where one of the strings has invalid UTF-8, like say you have UTF code FFFF and it's invalid, what do? Well, there's three things you can do. You can either throw out the whole record and say this record is invalid, it contains invalid data. That's the safest way. You could strip the invalid data out and just keep the part that's good, or you could convert the invalid ones to the invalid character rune in Unicode. So if you have all of these different systems, let's say that your system at the database layer that's actually storing your records strips bad data out and just keeps the good data. Now that means that if in your login system or in your admin system, you say, I want to add a user and I want to add that user and add him to the group admin Unicode FFFF. Now your system says, okay, well, that's not the admin group, so I'll let him use that. So it goes and stores that in. Now on the upper level, it thinks, okay, I'm just adding him to this, I don't know what username. And then it gets to the database layer. The database layer now strips the FFFF and stores it as admin. Next time this guy logs in, he's an admin. And these kinds of issues are going to keep on cropping up, and it's going to become more and more of a problem. And the problem is, since these hackers are no longer just these little script kiddies, they're all state actors, they're all paid actors, they're people who have a vested interest in breaking your system. This is going to become a huge problem. So one of the things that we have to do now is we have to tightly specify these. And with JSON and XML and these guys, the barn doors are already open. These are the old guard. They have to go away. We have to replace them with better systems. Next thing, yeah, native support for all common types. We shouldn't have to coerce things into strings. That's just asking for trouble. That's asking for incompatibilities. And once again, you end up with the not tightly specified enough problem. Future proofing, meaning that every document stores a version to say, this is the version of the specification that I adhere to. That means if I need to deprecate something later on, or if we need to add different types of things, you can say with this document was for an older version. I have to use an older version of the codec to decode it. And then the newer ones, the older codec can't decode it. You have to use the newer version. Low energy size, low energy and size impact, because I mean, come on, we're like in 2021 now. We have an ecological crisis on our hands. We need to really reduce our energy footprint. No definition files or code generation steps. That's basically what I was talking about up here with the record-oriented ones. That's great if you want to be dealing with record-oriented things. There's nothing wrong with this per se, but when you're just dealing with small data, you really don't want to be having to mess with this stuff. Okay, I'll show a very quick rundown of examples of how this looks in practice. So we have all of our different numeric types. So you have the Boolean type, you have integer types, which can be represented using all of the different formats that are common to what you would expect to see in C, for example. So in binary format, octal format, decimal, hexadecimal, they can be really, really long. There's no limit to how big this thing can be. Floats can be written in decimal format. They can be written in hexadecimal format. If it's in decimal format, it stores that exactly. So if you have 0.2, which can't be represented in IEEE 754 binary float, with this, it can. It stores it exactly. Not a number, infinity, etc. Different string types. URLs have this sigil at the front of them so that the system will know that it's a URL and not just a string. UUID is very important. It just recognizes it from the dashes in the structure here. It knows what it is. Dates are first-class citizens. Once again, This here, don't worry too much about that. That basically just means that if the system was able to find all of the data except this one piece of information, it says this information is not available, and here's the reason why it's not available. And then the client can decide, okay, well then I don't want this record or whatever. Containers, lists, maps, what you would expect. We have arrays, and the arrays are typed, so you can have a byte array, an integer array, etc. Markup, that's just basically does the same thing that HTML would do. I won't go too into detail with that. References are important. You can mark an object with a name, and then you can refer to it later on. So if you have repetitive or cyclic data, you don't have to worry about this. This does not have to be an acyclic graph if you don't want it to be. Speaking of graphs specifically, you can actually have a graph structure here with vertices and edges and whatnot to represent all the different structures. Trees here, you can represent a tree exactly. So you can see the 2, 7, 2, 1, 2, blah, 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 blah. That's not terribly important for this discussion though. Constants, and then custom types. Of course, if your type is not represented properly, you can have a custom type. This will hurt interoperability, but you would basically say, put in a schema and say, in this schema, here is the data type, and here's how it works. And as long as the client knows what to do with it, it can store it. If it doesn't know what to do with it, then it would be up to the user to say, well, throw it out or whatever. So that's basically how the text format looks. The closest competitor to what I am doing is Amazon Ion. They actually had the same idea of having a text and binary format that was compatible with each other. So that was pretty cool. But there were a couple of things that turned me off. One of them was that the binary format is in big Endian format. And we don't have big Endian CPUs anymore, which means that all of the systems that have to talk using Amazon Ion are going to have to convert to network byte order and then back to host byte order every single time, which is wasteful. There aren't as many types. There were a few types that I wanted that were not there. Typed arrays, so you can't have like an array of integers, an array of floats, those kind of things. No time zones, that's very important. We need time zones for time. We need to know exactly what, that this time zone was taken in Berlin, or this time zone was taken in San Francisco or New York or whatever. They don't have that in Ion. No BC days, that's not that important. No leap seconds, that is important. You can't store 61 seconds in Amazon Ion. I don't know why. No beat float 16, that's important because all of the new AI systems are using it. All of the new CPUs are adding this type. So this is going to be very important coming in. Lists must be prefixed with a length. This is problematic because if you're generating a list programmatically, you don't know how long it's going to be. So in this case, you can't build the list because you don't know how long it is yet. Map keys must be strings. I didn't like that because I wanted to be able to support, integers or floats or whatever type you want as the key. Okay. Any questions about that so far? I'm going to go into the Go implementation next. Everybody cool? All right. So yeah, so for the reference implementation, I'm doing this in Go. My goals for this were for it to be as efficient as possible, obviously, because I want it to be used, but also modular so that I wouldn't have things rigidly stuck and I could mix and match, because I've got two codecs. I have a text codec and a binary codec. They both need to follow the same rules, and I don't want to have to write the rules twice because that's just asking for trouble. I'm going to have bugs left, right, and center dealing with it. Also, when I'm testing the individual components, I want to make sure that I can test them in isolation. And the only way to do that is to make this modular. I'm using a SAX style, which is the simple API for XML style, which is an event system where every time the parser reads a particular, in XML, when it reads a particular tag, it generates an event for that tag and says, I encountered this tag. It had these attributes to it. These are its children, blah, 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 blah. I'm following a similar model because it works quite well. And obviously out of the box support for almost all Go type structs and containers. It doesn't support complex, but I did put in an example to show how to support it if you want it. So the example here, let's see if this actually works. And it did work. Okay, so this is just to demonstrate the user API to this, how you would talk to this thing and make it do stuff. So right here, I just created a quick little dictionary. I did an interface to interface because I've got different types of keys, different types of data. So I've got a string, a float, an integer, and a date inside there. And then I create a buffer as a output stream. And then I basically just say, okay, marshal this dictionary to this output stream, and then print out what I got. And that's basically how you use it. And then when you want to unmarshal it, you have your data. And then I'm just saying, okay, fine. So let's just assume that this is the data that came in. You take that, you take the bytes and you just say unmarshal that. And then that gives you your value, which is your dictionary. And that's what you get here. So this is what the concise text encoding format looks like for the same data. And this is just the basic Go print routine to show what the dictionary itself looks like. And then I have the same thing with concise binary encoding. So it converts it to binary and then converts it back again.
Looking at this from like a JSON perspective, this looks like pretty printed, but it's kind of the one and only, or like there is no difference between like, you know, print that or print the text version compact or something.
Yeah, I started doing that and then I thought, no, that's actually a bad idea to do that. You do not want to minify concise text encoding because it's not designed to be transmitted. You should not be transmitting the text. You should be transmitting the
okay. And it makes it simpler, like you just have like this one.
Yeah, it's simpler because now whenever, like for all the text editors, if they build editors, you know, the editor additions for this particular format is like, okay, well, it always looks exactly like this. Every single time anybody sees a CTE document, it always looks the same. Okay, and oh yeah, an important thing here. Now, let me run this again. Oh, did I run it here? Yeah, I did run it here. So an interesting thing here is this is basically the identifier. So that's the first byte of a concise encoding document is going to be the small letter C for a concise text encoding. The next thing is going to be the version number of the spec. It's currently 0 because I haven't released it. But this can be like as big as you want it. I could have 10,000 releases and this would still work fine. And then there has to be white space and then the object, whatever it is. That could just be like, you know, C0 space 1 means that it's a concise text encoding document containing the integer 1, and that's it. But generally you would put like, you know, a map in there or something like that. That's why you have that C0 at the top. Okay,
here's a short question in the chat, I guess.
Oh, sorry.
Which languages? No problem. Which languages are supported?
Right now, it's just the reference implementation that I'm writing in Go. If anybody wants to help out for other languages, please do, because I've only got so much time on my hands.
Yeah, sure. I think, people can view this as an invitation or just to.
Okay, so the architecture that I have, the high-level architecture that I have for the Go project itself, we have 5 main sections to it. So you have the events, the iterators, builders, the codecs, and the rules. Everything follows the event system, and it basically uses the event data receiver as the interface. So that's what this guy here is. So this data event receiver interface can receive any event from any other component, can talk to it and say, I received a begin document, I received a version, I received an integer, I received a list, and this list contains blah, 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 blah. And so when you are building up a document, actually, I thought I put something down here. So when you're building up a document, for example, this one here, you would have the event begin document, version 0, map, string, a key, and then float 2.5, integer 900, date, this date, end. That's what you would see here. So end ends whatever container you're in, so that it goes up in stacks, and then it goes back down again whenever you close a container. So yeah, so whenever you're unmarshalling this document, that's the order that you would receive these events in. So as long as you can implement an event receiver, you can receive these events, and then you can understand what kind of document it is that you're dealing with. So an iterator will basically consume a Go object and produce a series of events that describe whatever that object was. If it's just like an integer, then you'll just receive a single event integer. If it's a struct, you'll receive map because it doesn't understand what a struct is, and then it will have, you know, all the names of the name of the field value, name of field value, name of field value, end. Builders will consume the data events. They are a data event receiver, so they will receive these events, and then they will produce a Go object out of it. And then the codecs are also data event receiver or data event producers that will convert, you know, the on-disk format to events, or events to the on-disk format. And then the rules, this is where I was talking about, you know, I don't want to have to write two different versions of the rules. So the rules themselves are data event receivers. You basically put that in front of whatever it is you're working with, and it receives the event, decides whether it's valid or not, and then passes it on down the chain. And so you can have a long chain of event receivers to do whatever it is you want to do with when you're receiving these events. So quick example, iterator is actually just defined as a function. There's no object oriented or anything like that. It's just a function. It has a context, and the context just has some helpful things for it to do the work that it needs to do. And value is the value it has to fill out. It has to use reflect because of limitations in how Go works. Reflect is slow, but this is kind of the best you can do. I took a lot of cues off of the JSON codec that's already in Go, and that's actually really fast. They have optimized the hell out of that thing. So I took a lot of hints off of what they were doing. Yeah, so for an example, if you wanted to iterate an integer, you would say, okay, v is actually the integer that you want to iterate. So it would say, okay, in the context with the context current event receiver, whatever the context is pointing to for the event receiver, send it the on int and pass it the integer value. And that's basically what this thing does. All of the iterators are just going to call context event receiver and tell the event receiver what they've encountered. Iterate interface is a little bit more complicated. There's a special case where I had to put some special code in here because reflect value can actually contain invalid values where the original value was null, but the reflect value is actually invalid. And if you try to dereference it, or you try to even check is nil, Go will throw an error at you and crash your program. So you got to be really careful dealing with that. But yeah, don't worry too much about that stuff here. Here you are saying v is a reflect value. Since it's an interface, you have to grab the element out of it. This is part of the reflect contract, and that gets you the real value for it. Then here's the tricky part. I tell the context, okay, fine. So for this element that I've pulled out of the interface, we don't know what it is. It could be a string, it could be an integer. We have no idea. So we tell the context, okay, fine, inspect the type of this element that I've just extracted and generate for me an iterator that can iterate that type. And I'm not showing how this works because it gets really, really complicated under the hood. But basically, I have this caching mechanism that will generate iterators for any given type that it hasn't seen before. And if you pass it a type that it has seen before, it's cached the iterator for it, and it'll just pass that back to you. And that helps it get a lot more speed. So when you get the element, you get the iterator, and you just tell it, iterate this. And that is the entirety of iterating for an interface. Pointer is kind of similar, except that, why did I have to do it this way? There were some issues where I wasn't, oh yeah, that's right. So since pointers are typed, every single pointer has to have its own iterator. So a pointer to string has to have an iterator. A pointer to struct A has to have an iterator. A pointer to time has to have its own iterator. So I can't just make a generic iterator function like I can for interfaces. I have to go inside here and say, okay, generate a new pointer iterator for this pointer type. And then it will, and then return a function, which is your iterator once again, because it follows the same contract. So this is where it starts to get a little bit more complicated. Then we get into stuff like maps. And it gets a little bit more complicated because now we're saying, okay, we still have to return a function because every map is going to be different. You're going to have a different key, a different key type, different value type, which means you need a different iterator for it. This is where having generics would have been really helpful in Go. But since we don't have that, I have to say, okay, get me an iterator for this particular key, get me an iterator for this particular value. Now return an iterator function that uses those particular values. And then struct gets even worse. This is where we're getting super nasty, because now you have to go through here and go into the struct first off, find out how many fields it has, build a fields list out of that, step through all of the individual fields, check to see if it's exported, because if it's a private field, you can't access it. There's all sorts of crazy things that come along. And so this first part here is just to fetch all of the individual fields and generate all of the individual iterators for each of those. And then once you've done all of that stuff, then you can generate your overall struct iterator function. And I'm not going to spend too much time on this because it gets really, really hairy. And I spent months and months and months trying to sort through all the bugs that I generated dealing with that stuff. Builder takes everything the other direction. So if you could actually take an iterator and plug it into a builder, so you could pass in like an integer to an iterator to a builder, which would generate an integer and sort of thing. So these ones here, it has functions where it can build from all the different types. You can say this builder, I have initiated a list, I've initiated a map, I have ended a container, et cetera, et cetera. It looks very similar to the data event receiver here, but it has to be slightly different because the builder needs to keep track of the context and it needs to know the destination value that it has to fill with whatever it has generated. So unfortunately, I couldn't keep the exact same structure as I did before. So for example, here, generating a Boolean. Now this one here, I have to use a struct because it has to conform to this interface. So since Boolean is so simple, I can just have this global builder, and then when I call the generate bool builder, I just return that global builder. It's really easy. And then I say build from bool. Here's your context. Here's the actual value that you need to generate, and here's where it needs to be. You just call destination set bool value, done. Slice is a little bit more complicated because you need to know what your destination type is for the slice. You need to have a generator for the elements themselves to be able to fill them out. And so every single time you, so when you begin list contests, so it will say begin list, here's the context, here's the contents that are going to fill in your slice, and then you end the container here. So it will go in and it will, oops, where are we here? Yeah, begin list context. Here we go. So you'll have a begin list context. It stacks itself on the stack to say, okay, I'm one level deep for this particular slice that I'm building. Then you would send in build from bool. So it would say, okay, generate a new element. The new element is based on the type that you stored before, which is, in this case, is Boolean. So it goes this Boolean type, generate an element. And you have to do this with this reflect new dot element, where you're generating a new pointer to that type, filling the type, and then taking the pointer and getting an element out of it. Because if you don't do this, then, and you only did this type element, Go will generate a non-addressable value. And as soon as you try to store this somewhere, it'll throw an exception saying that's a non-addressable value. You can't do that because it tried to allocate it on the stack. This is how you force Go to allocate it on the heap. And then you actually grab the element itself. And now you can get the address of it without it blowing up in your face. I found that out the hard way. I had to do double pointers here because slices are a little bit tricky. It's not giving you a structure in and of itself. It's just giving you a pointer to a memory location and a length. And anytime anything changes on it, or if it has to reallocate or something like that, now the old address is no longer valid. So I've had to store the address to the slice in order to keep track of what happened to the slice whenever it grew and shrunk and reallocated on itself. This is getting really, really complicated. So I'm just throwing that in there as an aside to say, when you're dealing with slices, you have to be really, really careful in Go, especially if you're trying to keep the address of these things. So anyway, the idea here would be that, yes, you get begin list context, it stacks itself, you store a bunch of things. In this case, I've only shown the bool thing. You build from bool, you generate a new element, you call your element generator build from bool, which is going to be the same thing that this guy did here. So it calls build from bool, it just goes and sets bool on the destination value, which is, in this case, this object. So you're saying, take this Boolean value, store it in this object. And then once that's done, you call store value. This is where it goes and tries to append it to the string, to the slice, and keep track of if that particular slice happened to reallocate because you ran off the end of its capacity. And then once everything's done, then you do build end container and it says, okay, fine, I'm going to unstack myself. And then I'm going to notify the parent object that I am done. And then the parent object can say, okay, this object that happened to be a slice is finished. I can store it and then move on. Map builder is where things go really crazy. And I'm not going to get too much into this. You have to generate. You have to store the different types. You have to build generators for the keys and the values. You have to have a storage for the container. You have to keep track of the key. You have to keep track of whether you're storing the key and the value. It gets really messy. So we'll just gloss over this part. Struct builder is even worse. This one here, you have to keep track of all the different descriptions about what the fields were, what type they were, what generators they had, how you keep track of whether you're reading from a name or from a value, how you get access to the value from the structure itself. It's very, 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 very messy. I'm just throwing it in there just as an illustration to show just how crazy this stuff gets. Okay. Any sort of questions about how the structure, how the architecture and stuff works?
You mentioned rules in the architecture, but didn't show them, I think. So my question is, I often encounter structs that I need to transmit to other services. For example, I have a client that wants to place an order and has a quantity, and I thought about it would be cool if I could say the encoder to constrain the quantity field, for example, to a specific range and fail if it has exceeded also.
Yeah, so that would be the job of a schema to say these are what are valid within it. The rules seen for here, that's to enforce the structural rules of the concise encoding format itself, to say that you can't, for example, store two strings together. Well, you can't break the structure of a map, for example, and store things that are not supposed to be in a map, or you can't suddenly start an array and then suddenly have a map inside of the array or something like that. There's certain structural things that are just not allowed by the format itself. And so the rules will enforce that. But if you want to enforce specific values, or say that you can only build a structure that has these fields in it or something like that, or if this field is set, this field has to be 0 or something like that, all of those kind of rules would be defined in a schema. And then you would publish that schema so that the client side can also validate before even sending it to you and say, okay, the schema would validate and say, am I sending a valid message to you, yes or no? And of course, you would have it on your side too, just in case they sent it anyway.
Is this somehow already supported to define schemas?
No, that's something that I'll be adding in later. But since I have this data event receiver interface already, when I do implement the schema, that will be, you'll have the rules in the first part of the pipeline. Then the schema interpreter will be in the next step of the pipeline. And then at the end of it would be your builder, which would build your structure in memory in Go, for example. And so if it's able to pass the rules and the schema, then it goes to the builder and the builder builds it.
Cool.
And I can show actually really quickly what the rules looks like. Oh, here's what I mean by the generated stuff. It's a lot of generated code. This is where generics would be very, very handy. Let's see. Okay, rules array. So for the rules, let's see, what do we got here? Where do I have something where I can fail? Maybe that's not the best idea.
Quick question.
Yep.
Yeah. What that mean? Underscore this is this what?
Oh, I'm just using that for just to represent the struct itself.
Okay.
I'm a bit old school in that regard. I use this.
Okay. Okay.
Yeah, let's see. String length array. Yeah, okay, so let's see. Array type. Yeah, so if you receive like a string length array, which would be a string or a URL or something like that, this thing will assert that the type is allowed for a particular, like is allowed for this particular type of array coming in. Because if somebody were to start a string length array and pass in and say, this is a string length array of float 32s, for example, that's not valid. You're not allowed to pass in a string array of floats. You're allowed to pass in a string array that contains string data, character data, and that's about it. So this rule will check and see that the array type that you're actually passing in is correct. And then the next line here is going to call a string validator to check the UTF-8 data itself, make sure that these strings are actually valid UTF-8 strings. And concise encoding is set up such that it will reject anything that is invalid data. You do not accept invalid data. This is part of the security side of things, where anybody who accepts invalid data is taking a huge, huge security risk. It's better to just throw it out, reject the whole thing, and tell them, do it over and do it right, because I don't want to take on the security risk of this. So all throughout this code, I have code where if anything is amiss, I throw it out, literally, and throw it back in their face and say, error, you got to redo this.
Is the error stored in the context and then passed down the stack?
It's actually thrown. It's actually thrown out. It's thrown back. So I'll raise an exception. Sorry, I will panic. And then at the top level of each of my internal APIs, I have a thing that will defer, check to see what the type is, and if it's the right type, then it will generate an error message, nice little touchy-feely error message for the user. If it's a complete total programming error where it's like a Go thing, then it'll go all the way up and blow up. But if it's something that the user has done wrong, I will panic. It will catch in the defer, and then it will put a nice message for the user.
Yeah, that's interesting, because it's somehow uncommon, but this is one of the examples where raising a panic is probably better than annotating every method with an error return value. Yeah, so I think that's quite a good decision to do it like that.
Yeah, absolutely. Switching, I mean, at first I was doing it the way of checking return, like checking error code and all of that. When I switched to panic-based runs, I improved the performance by 30 some odd %, just from moving to that. So you definitely don't want to be exposing your users to panics. But if it's a purely internal API that you're only dealing with yourself, or if you put a big fat warning on it, which I have done here. Let's see. So for iterator, let's put those small. Oh wait, no, it's better actually for me to use this one here. Encoder, no. Hang on, I got it here somewhere. New encoder. Yeah, I had some internal APIs where you can actually access it. Oh yeah, here we go. Yeah. So I will say, note, this is a low-level API. You have access to it. You can use it if you want, but you have to be ready to receive the panics for it. I have at the top level, I have this concise encoding top level where everything, normally what you would want to do is you'd want to use the marshal and unmarshal interface. That's what most people are going to use. And that returns type error always. Same with the unmarshaler. When you get into the encoder decoder, now you have to deal with a lot of these things yourself. So some of these can throw, can panic, and you have to be ready for that. Oh, this one here actually still does return errors. So that's what I did at that level. But yeah, once you get to the actual nitty gritty, then yes, it will panic, and you have to be aware of that. But I've put all these warnings all throughout the code wherever you have to deal with it. And what else?
Just a short, like, I'm not sure like whether this makes sense. A question like the encoding and decoding side are like the two sides and represented by iteration and building.
Mm-hmm.
Which one do you consider like more complex?
The builder is more complex,
like
definitely.
The builder.
Yeah.
So writing it, reading data and building the Go objects.
Yeah.
Is basically
that
the more complex side of
it. That's absolutely the more complex side, and you can even see it from the code itself. Like just the iterator I could implement as a function for everything, where you just use a function type. Here I had to actually have a struct. I have to store state all over the place, and it just, from a functional perspective, it feels absolutely horrible. It's so impure. It's really nasty. But when you're dealing with data communication, you can't get away from that, unfortunately. So yeah, it gets really, really messy really quickly when you're dealing with building from deserializing from your serialized format to actual objects in memory.
Yeah, I had like some impression of that. Like I wrote some tiny encoder, like taking a value and encoding it, and it was kind of like relatively straightforward. It was like not too super easy. But,
yeah. I think my builder code is probably, well, yeah, it's huge already, and I think there's probably about 3 times as much code as there is in the iterator. Well, you can see here. So there's the iterator. It's just a few little functions here. There's builder.
Yeah. And another question, maybe this is just like for my understanding, but my first idea would be to use, like, for example, slices are, like, I learned about slices like recently, or relearned some of the things, like they are 24 bytes and they have like, they are just like a tiny little blob of data, basically. But so you are building that yourself, and you have to deal with the implementation details a little. Like, I'm not sure, like, is it the implementation detail of Go itself, like how the slice is represented? Like, you have to access that. Would it be possible to not worry about that and just like append to the slice, or like just allocate a slice and then just append to that? Or like, is it a performance thing? Is it like not possible? Or I'm just misunderstanding
with the slices. Yeah, so with the slices, it was I had to have 2 different references to the same slice. So I had to be able to reference it from 2 different locations, and that's where the problems come in, because as soon as the slice reallocates, one of these 2 references is going to be invalid. And so in order to keep track of all of those things, that's why I had to do that double pointer indirection trick
Good.
for it.
Yeah.
For most people, you're never going to have to do that kind of crazy stuff. But when you're low level, it becomes inevitable at some point.
Yeah, they're like really crazy gotchas that you can
Yeah.
construct. Okay, thanks.
Yeah, so I guess we're coming close to the end here. So I'll just talk about my takeaways for it. I mean, for me, there was a big learning process in using this. The biggest thing that I learned is that memory allocations are your enemy in Go. They are the enemy. That is the number one cause of slowdowns in your app is memory allocations. And these memory allocations happen everywhere. And the only way to get rid of them is to actually profile your code using the Go profiler, use the little graphical display thing, and check and see everything that's calling malloc and try and find ways to stop it from doing that. The less mallocs you call, the faster your code goes. My code is now running just from the allocation optimization. My code is now running 5 times faster than the first iteration was, just from the allocations. None of the actual logic had changed much since then. The number 2 thing is strings and byte slices. Whenever you convert between them, there's an allocation happening in the background, almost always. And those just kill you, especially if you're dealing with any kind of encoding system or any kind of text processing system or anything like that. If you're going to be processing text, you want to keep it in a byte array, in a byte slice for as long as you possibly can. And only ever switch it to an actual string when you absolutely have to. It was the only way I was able to get around this issue, was to keep everything and I had to change my APIs internally so that they always passed byte slices. And I only ever switched to a string when I absolutely have to. Next one, caching is absolutely essential. Modern processors now, cache locality will kill your performance faster than anything else out there. There's nothing else. I mean, other than, of course, the memory allocations in Go, but for all other languages, cache locality is the king. That is the one thing that determines whether your program is going to run fast or it's going to run horribly slow. And I had huge problems with cache locality when I first started, because I was using, the old school style of programming where I'd have long arrays of things. And of course it would step through the array, and then it would get about 3/4 of the way through the array. And then it would be cache miss, cache miss, cache miss, cache miss, cache miss. And my performance would just drop through the floor instantly as soon as I started doing that. And once you get into a loop where it does that, you're running at maybe 1/100th the speed that your CPU is capable of. It's horrible. So yeah, keep your related data really, really close together. The closer, the better. Keep your most important data all together so that you can have some core of the most important data that's used the most often together, because that's going to go into your level 1 cache, which is really, really small. And then, you have level 2, level 3 cache outside of that. A level 1 cache miss will cost you approximately 50 instructions worth of time. A level 2 cache miss is getting up to like 500, I think. Level 3 cache miss, you're into thousands. Like it's just nuts how it is nowadays. Next takeaway, Go really needs generics. I have tens of thousands of lines of generated code. I have custom code generators that I had to write to be able to deal with all of the issues with all the boilerplate that I would have had to write otherwise. If I didn't write code generators, I couldn't write this program. Just not possible. Or if I did, it would be horribly buggy. What I would love to see read-only values that you can define, like normally if you wanted to define, for example, an array that's read-only at runtime, say a global array that you want to be able to use for reading and for reading from only, you can't define that as a val. You have to define that as a var. It would be nice if you could do it, C const style, such that you can say this is read-only, so that you don't accidentally write to it. So read-only stuff, that would be a really nice thing that I would love to see in a future version of Go. And yeah, there you go. Hope that wasn't too long or too deep.
Oh, thanks. Thank you very much. Great presentation.
Thank you.
I think Yeah, and a fascinating subject, at least for me, because I don't write these things. I mean, nobody writes encoders all the time. It's probably a special topic, and yeah.
And requires a special kind of insanity, yes.
Yeah, yes, or I would like, yeah. So I probably have a couple of questions, like just like I think you motivated this whole project very well in the sense that like yeah, security issues and yeah, I think these things will just get more important. I would be just curious, like you had like about the process of like how this developed over time. Like you had this idea, you looked at example projects, you looked at other implementations. Where did you get your ideas from? Like, do you have like some sources or the experience, like how you represent types, which types to put in?
I
Version one, like
actually, yeah,
or like
there was actually this one talk given by one of the Go core devs, talking about how he had implemented the parser for JSON.
oh, that's
And
interesting.
yeah, I don't
Is
have the link offhand, but if you search for it, I'm sure it's somewhere on YouTube anyway. It's a very fascinating talk that was hugely influential for me. And I was originally going to try and do some kind of EBNF type, or sorry, some type of generated parsers, like Bison style or something like that. And I did have that at first. I was using Ragel to generate the text parser, and it works, but it's just after a while you have enough edge cases that are specific to your use case where it just doesn't quite do what you want, and you can kind of coerce it to do it, but it starts to get ugly. And then I saw this talk by the Go dev and saw how they were doing their JSON parser. And yeah, I was instantly hooked, just how they were dealing with it, how they were taking advantage of tail call recursion, how they were using function pointers to be able to call the individual functions and then passing it along in a long chain. You really have to read the have to view the video to get a true appreciation for it. But that was a big thing. And even when I was developing the text parser for it, I was knee deep in the Go code for the JSON parser and encoder. I mean, they've done a bang up job. That's a really well done for such a horrible format.
yeah, that everybody uses. Like,
yeah. Well, everybody uses because that was the savior from the XML mess. So now we need a savior from the JSON mess.
Yeah, which reminds me of this interesting document, "Worse is Better," which is like I'm not sure like people are familiar with it, but there's this like term "worse is better," and some things succeed even though they're worse, just because of timing or some other properties.
Mm. Yeah, I mean, it's not just like JSON. I mean, it was a godsend. When it came out, what was available was terrible. It was the same thing with XML. When XML came out, what was available at the time was terrible. It's just you have to make these leaps, but you can't make a leap from 0 to 100. You have to do these steps along the way.
Yeah.
And I mean, if uptake on concise encoding happens to the point where it becomes ubiquitous, I'm sure in another 10 years, somebody's going to look at my stuff and say like, oh my God, that's terrible. We got to fix this.
Yeah. Yeah. So you've been like I'm just asking like more questions. Like people should like I'm open. We should just do Q&A a little bit if you want. So you implemented the Go implementation and you have like a spec which is kind of fixed. I assume like the version 0, which is kind of still have room for changes, but it's not the version 1 like something. So I believe it's
version 0 is basically I reserve the right to make breaking changes.
Yeah.
And then once 1 comes out, I will not make changes.
Yeah. Do you have a roadmap or like do you plan like, okay, now I just want to put it out and people should use version 1 and here is the reference implementation. Do you have a plan for that? Or I mean, I understand it's a side project and it's kind of like you're doing it for learning and your own
Yeah.
pleasure. But
Yeah, the general idea is that I need to get more eyes on it. I need to get more people critiquing the format itself. I've got one guy, one really cool guy. He's been really prolific, and pointing out all the flaws and things that I have in it, because it's you can't do it yourself. You need more people to be able to point out the issues that are going on. If I didn't have this guy pointing out the flaws in it, I'd probably be, at version 10 within the first year. So the more eyeballs that are on this thing, the better. And I'm really hoping for a good 1.0 release. I'm hoping, maybe Q2 next year to have the V1 out. That's my hope. But it all depends on how many people look at this.
yeah. I mean, and I think, it's also fine for just, letting it develop and making it stronger over time, especially
Yeah,
with a side project, and especially when it deals with something that should be like probably, if it's once it's used, like people use it all the time or something like that, or it will be a core component of something. Yeah.
Yeah. And I mean, even if the 1.0 turns out to have flaws and stuff like that, it's versioned anyway. So we'll just release version 2 and then version 3 and version 4 or whatever. I mean, the main reason why I put this whole versioning thing is because I just don't trust myself. I know I've made a ton of mistakes on this, and I know there's going to be a bunch of things come back to bite me, and I want to make sure that I can fix them.
Yeah, that's, sometimes in JSON, it's kind of mentioned as a feature that they don't have versions, like it's just like this single thing, but certainly, I think, I think protocol buffers has like some versioning.
Protocol buffers have versions, and then
and it's kind of not.
Yeah, I think in my opinion, it's essential. You absolutely have to have that, because otherwise you can't deprecate, you can't make changes.
Yeah.
And that could be a feature, but I think in today's day and age, a mistake that could lead to critical security issues is a fatal mistake. And if you can't change your format to suit it, then your format has to die.
Yeah. One interesting thing that I find, or like one thing that I find attractive, is that, of course, like we deal with a lot of uncertainties in the data in code, and it's always better to push that somewhere else, like maybe in your database schema or your constraints. Like I think I heard like stories from guys who put like all the logic into the database so that all code outside is kind of cleared of that. And I think that it's interesting, or like useful. It's another way to think about it. Like if you think about JSON or XML, you might think about like, okay, but here are the edge cases that I have to deal with in code. And if you can push that format, it would be a good way forward, I think.
I've worked in places that do that, in enterprise places where they had a gigantic Oracle database with all of their logic stored in the database itself. And it kind of works, but it also comes with a huge set of problems and issues and things. So
yeah, probably.
I think there's the problem is the complexity is there, and you have to deal with it one way or another. And where you deal with it can be important or cannot be important. You have to be really, really careful about what decisions you make about where you're going to be doing your logic and where your complexity is. I'm more of I'd rather have complexity code side, so that if the data storage turns out to be a problem, it's easier to swap out. Once you move your complexity into the data storage system, it becomes a lot harder to move to a different one if you discover a fatal flaw in it or something like that.
Yeah. True.
But yeah, there's definitely arguments on either side. There's a lot of happy Oracle customers who have all of their business logic in the Oracle database itself, and they swear by it. So it depends on what you want.
As a side note, not only Oracle, but I did a course on Postgres, and also did some PLPG SQL is language called in Postgres, and you can do a lot of fancy stuff in it. And I think it's really fast becomes very obfuscated what the actual logic you are implementing was. And I would be, you have to think very deeply about what to implement as custom logic in the database, and if you need it there.
Yeah, absolutely.
Explicit is better than implicit. Oh no, we are at the Go meetup, not at the Python. Yeah, just like, I mean, everybody should like feel free to ask questions. I'm just kind of moving on a little bit to the Go implementation and to these takeaways, which I find also really interesting and helpful. Interesting also to worry about these things. I worry about some of these things also, like I see the difference between like the scanner and the buff.io reader, like there's the difference in number of allocations and it's visible in the benchmarks really like obviously. Are there any like you mentioned pprof and the pprof for memory allocations and CPU time that you spend maybe in certain parts, or like just the CPU time for malloc or something like that? Are there any other tools that you use or any other tools, libraries that you use for that, or
No, I just use the I just use the ones that come with Go. The tools that they have for it are actually really nice.
Yeah.
I mean, you've got a thing that can do your profile for you. I've got a little make file where I just generate where I just run them. Actually, let's see if I can pop them up here. Yeah, so there. Oh shoot, I can't remember how the heck I did that.
Yeah, I don't remember the incantation. I forget if like -wab or -png or something like that.
There was one that would actually, oh yeah. Web. Oh, no, that's not what I wanted you to do. Where did it put that? Prof1. Okay. Trying to load them in the wrong tool, but
I think you can generate also a PNG, but then it's not that zoomable maybe.
let's see. Oh yeah, I was trying to open it with the wrong thing. No, don't start Windows. All right. Go away. Open with, actually there should be a preview thing in here, but no, well, this one. There we go.
Yeah.
Yeah. So this, so what I mean, the biggest thing, of course, as you can see, there's a like malloc, even now, after I've made all of my optimizations, it's still having a fairly significant impact.
Yep.
So in this case, everything that's underneath here, this is all system stuff. You don't really worry about that too much. What you're worried about is everything that's pointing to malloc. New object, you're probably not going to be able to deal with anything. Here we go. Slice byte to string. This is evil. So this is one where I had a slice byte and I had to convert it to a string for some reason or another. And that causes an allocation every single bloody time. And it just kills your performance. So you have to keep that down to a minimum. So I was calling that from inside here, but this is a build from string like array. So I had to, in this case, because I'm building a string. But let's see. Yeah.
I mean,
yeah, I think I've already plumbed the depths of this thing, but normally what you would see is when the first time you run this, you'll see like a couple of gigantic boxes here saying like, this is taking 60% of your time or something like that. That's what you really want to be looking for. Deal with the low hanging fruit first and try and get things down to the point where they're not taking more than say 15% of the total time.
Okay, I recently discovered a very useful flag for the go to a pprof, especially if you're looking for regressions, and there is a -diff flag. I'm not sure if you know that, but you can pass 2 profiles and it will show you the diff between the two then. I will write an
Yeah.
example in the chat, and you can also normalize. There's a minus normalize flag, which normalizes it to 100% or something. Yeah, it's really, really good to detect regressions.
Yeah, absolutely. Yeah. Yeah. There's so many parts of this preprof tool that I haven't even looked at.
Yeah.
So I've just been doing the ankle biter stuff myself.
Yeah.
Yeah, it's the same for me. Yeah.
Yeah.
But it's still, even the basic things are very useful for cutting down or like finding performance issues. Yeah.
Yeah. Yeah, this is probably my favorite part of the whole Go project is their debug tools and pprof and stuff. That's top notch. I mean, the closest I've seen to this is Xcode with their profiler that they have.
Yeah.
But even that doesn't come close to this.
Yeah, and it's kind of it works well for like offline things, or also web. You can also include it into web applications or web services. Yeah.
I do have one or two notes to the takeaways if nobody has any other questions.
Yeah, just go for it.
Okay, yeah. First, let me thanks for giving those valuable insights. They are very interesting, especially the thing about allocations between when doing string to byte slice conversions. I was not aware of this before. And one thing that you talked about was cache locality. And I thought about that there is a struct alignment. So depending on the order of fields in your struct, the actual memory consumption of the struct may differ. And there is some Golang X tool which automatically reorders your structs to get the minimal possible memory alignment overhead. So,
oh wow! Really?
Yeah, I have to look what the name of the Golang X tool was, but yeah, it kind of worked. And so have you already benchmarked or optimized your code in that direction?
I have in some cases in the structs. I generally, I mean, just from my C days, I generally do it like, largest to smallest. And so the smallest objects are at the end. So anything that's pointer is the highest level, anything that's integer, float is below that, and then bytes and bools are at the bottom. That's usually how I structure it. But I haven't done that too much in this one yet. I'm not quite at that point.
Yeah, there's a tool called Struct Layout. I think, you can print out the layout, and there's also a optimize flag or something.
Okay.
I guess what I referred to was field alignment, but I'm not really sure. Oh yeah, it's the field alignment tool. I linked it in the chat.
Ah, here we go.
Speaking about Go tools and libraries, one that I found also useful when dealing with my teeny encoder, which was exactly like, take away the Go object and serialize it, and it may be a struct. Then you have to iterate over the fields and all this stuff. There was a project. It's kind of not actively maintained, like Fatih structs, which basically allows you to wrap around, like you just pass in a struct, and then you can iterate over the fields or read out the struct tags or something like that. So it's archived now because I think the maintainer has a lot of projects, and he kind of at one point decided to take a break or something. But I think it's still like very usable for like probably non-performance critical struct munging. For example, if you want to implement your own tag, struct tag action code or something like that, this library really shortens the way there, because there's like a couple of things to consider if you just do it manually. But I'm not aware like how performant this is, like, because I used it for like not really that large scale stuff. So.
Yeah, it looks pretty cool. Actually, I did a little project a while back that basically subverts the runtime system to allow you to do all sorts of crazy things. Actually, I think I've still got it up.
Yeah. I looked at that repo and I found it really nice, but I have to look at it again.
Yeah, I had a lot of fun with that. I started monkey patching it so that I could change, the system system library functions so that they do different things, or that I could put myself, inject myself in between them and track calls to whatever it is I wanted to do. It can be quite handy if you want to debug something and you think there might be something wrong in the system level of it. You can trace what's going on without having to use eBPF or something like that.
Do people have other questions or comments on the encoding? There's a question in the chat. Have you tried for the byte slice string conversion unsafe pointer stuff? I was thinking about that as well. Like they're basically almost the same. Like I think string has like 2 fields and byte slice has 3 fields or something like that internally. And you could probably just.
I could do that. I've been shying away from unsafe just because that limits where the Go code itself can be used. I wanted the usage of this particular codec to be unrestricted, so you could use it as a WebAssembly app, for example, and it wouldn't be restricted. And as soon as you get into unsafe, then the compiler will reject that, of course.
Yes. Yeah.
But yeah, I was very, very tempted.
Yeah, actually, if you're writing smaller projects, that might be a way to go. If you're like not writing a library, but like the scope of things, and you just want to.
Yeah.
I mean, I use that also all the time. Like I have to convert to string for like some string methods, but in the end, I'm just interested in
what I have done. What I have done in the past is I've written a library where it would have 2 versions of the code, one that was unsafe and one that was safe, and then you would just pass in like no unsafe code or something like that, and then it would compile the slightly slower, of course, but safe version of the code.
You could probably also use build tags or something like that, your custom build tags, and
build tags, yeah,
or something like that.
Yeah.
Okay, any other questions or comments? Because otherwise I would stop the recording.
Here we have benefit.
There's another one in the chat.
Yeah. Would there be a benefit compared to encoding GOP if data used in Golang only?
I don't think there'd really be any particular benefit. I mean, unless this code happened to run faster, I wouldn't see any reason to use this over GOB. The only point where this is useful is if you need interoperability between different processes, different computers, different programs, that sort of thing. But you could technically use it in place of GOB, but I don't really see much benefit to it. Yeah, it is still missing other languages, of course, because, well, it's my personal project and I don't have enough people online to help.
Yeah. I mean, it's out there and it's good and it's documented, so I think people can read bit the spec, try it out, and
yeah. The repo is wide open for contributions. If you go on there, you'll see there's a lot of issues that this one guy has been opening up. I haven't received any PRs yet, but I'm totally open to that as well. So yeah, any contributions or anybody who wants to start, say, like a PHP implementation or JavaScript implementation of it or something like that, more than welcome to, and I'll give them all the help they need.
Yeah, great.
I have 2 short questions about the format examples. You showed the very long integer type, and I thought, is it possible to define it also as a hex format or in the binary format, or must it be the basic int example which is shown there?
No, it can be any format. The format that you write it in doesn't matter. You can put it any way you want.
Ah, cool. Then there is another question about the constants. Maybe you can scroll down to the section where you showed them. I'm not really sure that I understood how they work. So how, what type are they? Are they always a string, or yeah?
I mean, for constants to actually be supported, this is something that's going to be in the future anyway. You would have to have that constant defined in the schema, and that would define what the type is and what the value is. And then you could use it in your document, and it would require the schema to be able to get the real value and type.
Okay, okay.
But yeah, how to convert to JavaScript if there is no type for it? Well, that's just going to be the issue, right? If you don't have a type for it, you're going to have to find some way to cope, of course. And if you can't represent that type, you just can't represent that type. The idea would be that you would need to choose a set of types that are compatible with the systems that you're going to be dealing with. But I don't want to have to restrict everybody's types just because some systems don't support it.
Speaking of types, and you have the native, you implemented like native support for like trees and graphs, which are very useful data structures. Have you seen that in other encoding? Like, I'm not directly aware of like other encodings that have.
I haven't seen it anywhere else at all. I think this is, my personal opinion is just that this is something that hasn't been done, and so nobody's thought of any use cases.
Yeah,
I think that's the main reason, because the structures are useful. They're useful in memory. That means that they should be useful in encoded form as well.
Yeah.
And actually, there is something about this particular format. Let's see if I can get here. I think I did a little write up on this. At least I hope I have it in here. Let's see, structure. Node. Here we go. So it has a very specific structure in that it goes depth first, right to left, instead of the standard left to right. And the reason why it does that is because if you take this document here and you rotate it in your mind, you'll notice that it looks very much like the tree looks when you have it written, when you would have written it in pen and paper. And I have not seen this done anywhere else before, but to me, this seems to make the most sense, because then when you're looking at this document in text form, you can see what the tree looks like. If you kind of squint your eyes and turn it a little, turn your head a little bit, but yeah.
Nice. Interesting. Yeah. Any other questions, comments? If not, then I would just like, for the record, thank you very much for the presentation and for the project. And I hope if we publish this, then people see it and get interested and curious about that. And we'll take a look, a closer look. Okay, so thank you. Just stop the recording.
Thank you.